Welcome, everyone, for what's now our fourth session in the Electric Vehicle Center, what we're calling our surge session webinars. I'm Alan Taub. I'm the director of the University of Michigan Electric Vehicle Center, and it's really good to see people joining us today. And those of you who are in our December ones, welcome back. And people who are joining us for the first time, do make sure, and we'll show you at the end, that you register as an affiliate of our EV Center. It doesn't take anything to do it except going online. The U of M Electric Vehicle Center, we were formally established in 2023 with a $130 million grant from the state of Michigan and $20 million from the university. And our goal is to drive electric vehicle tech and talent, working with industry, government, and academia. And we do it in three main areas: technology, education, and workforce. I'm really pleased today to introduce our webinar speaker, Professor Greg Keoleian. Greg is the Peter Wege Endowed Professor of Sustainable Systems at the University of Michigan, and he's actually the technology pillar leader for life cycle analysis in the EV Center. He also happens to be co-director of the Center for Sustainable Systems and the Michigan Hydrogen Initiative. Greg's a true pioneer in life cycle analysis. In fact, when I was at Ford in the 90s, we were collaborating with Greg, and those were the early days when we had to explain to senior management what life cycle was. And so there's probably no one better in the world to talk about what are the life cycle impacts of vehicle production and use than Greg, and what we do about it. His groundbreaking work has in the past and continuing to inform policy, influencing industry practices, and we'd like to think now also impacting consumer behavior. And the key is electric vehicle and electrification of the transportation system is key to accelerating the transition to a sustainable energy system. Greg earned his degrees in chemistry and chemical engineering at the University of Michigan. He's recognized globally for his contributions, and he's being named to the Reuters Hot List of the world's top climate scientists. With that, I'd like to welcome Greg to take over and give us your webinar.
Thank you very much for the introduction, Alan, and I'm looking forward to presenting to our group today. This is a study that was sponsored by the UM Electric Vehicle Center, and the title of the presentation is Greenhouse Gas Reductions Driven by Vehicle Choices and Use Patterns. And we are actually presenting a paper that is in review now with Environmental Science and Technology. And these are my colleagues and co-authors. Actually, Elizabeth Smith did her master's thesis with us as part of this study. And other colleagues, including Alan and Chul Kim from Ford, contributed. So we're going to give you an overview of this this research, and the agenda first is really to, introduce the motivation and the need for climate action, which I think we're all appreciating, particularly with the California wildfires. I'm going to give you a short primer on life cycle assessment. If you're not familiar with that methodology, we'll review the scope, objectives, and methods of the study, and then get into some detailed findings and recommendations and conclusions. But just as a bottom line key takeaway, what we found is that increased electrification results in emission reductions across all regions. This is a new finding demonstrating the benefits of vehicle electrification across all grids and in the continental US. So in terms of climate change, it's driven by increases in greenhouse gas emissions, which are shown here. CO2 increasing over time since 1960, and the the IPCC, Intergovernmental Panel on Climate Change, concludes that warming is unequivocal due to human activity and our emissions. Recently, temperature rise was confirmed for 2024 to be the warmest on record, and getting close or exceeding 1.5 degrees C, which is a threshold for avoiding the most adverse effects of climate change. And the frequency of events is increasing. Weather and climate disaster events over $1 billion, as shown here by this NOAA graph. And you could see that these events, if you sum it up over since 1980, we're talking almost $3 trillion. And I think with the recent events in California, we'll definitely be at $3 trillion. And this is keeping track of drought, wildfire, flooding, storm disasters that are occurring across the U.S. This is 2024. There's going to be clearly a big impact in terms of dollars from California. So what is necessary is carbon reduction. And according to the IPCC, we need to reduce our emissions by almost 50% by 2030 and achieve net zero by 2050. The electrification of vehicles is a key strategy to get us there. In terms of emissions of greenhouse gases, we have transportation accounting for 28% of the emissions in the United States. Light-duty vehicles make up 57% of the transportation emissions, and that's where we're targeting, accelerating EV adoption to decarbonize the light-duty sector. Just before we get into battery electric vehicles, I just want to highlight in terms of strategies how we looked at actually fuel cell electric vehicles and compared the energetics, starting out with renewable energy, renewable electricity. And if you look at a battery electric vehicle, it takes 1.5 roughly megajoules going in of electricity to bring 1 megajoule of energy to the wheels. For a fuel cell electric vehicle, that's 4.5 going into the electrolyzer to split water to hydrogen, and then you have hydrogen going back into the fuel cell to make electricity to give you the 1 unit. So clearly, BEV is more efficient for fuel cell electric vehicles for light duty. There's other applications when there's issues of range or load where fuel cells can make sense. But for light duty, clearly the battery electric is the best option. Quick primer on life cycle assessment. So this is a generic diagram of a life cycle that starts with raw material acquisition, goes through material processing, manufacturing, use of the product. There can be service, maintenance, and then ultimately retirement, where you could have disposal and recycling, remanufacturing for a more circular economy. What we do in life cycle assessment is we draw boundaries around a system. So in the case of automobiles, we got raw material acquisition for aluminum production and steel, plastics, etc. And we track through the full life cycle and look at all the inputs in terms of primary materials, secondary materials, and energy. And then we trace all of the outputs in terms of emissions of pollutants, air pollutants, water pollutants, and the waste, as well as looking at the product and co-products. And we develop a profile. We have a set of metrics like life cycle greenhouse gas emissions, life cycle energy, and we get a profile to see how the impacts distribute across these stages. An example of this modeling we did on an automobile was very intensive. It was a project when Alan was at Ford. It was with the U.S. Automotive Materials Partnership of U.S. Car, where we broke down the vehicle, collected data on vehicle assembly, powertrain, breaking it down to the engine and engine block, to all the materials going in. This took 3 years to come to the result of a mid-sized vehicle, which shows the life cycle energy by stage, material production, manufacturing, use. And you could see 85% of the energy across the life cycle is in the use phase. And we total it all up to get the total impact. We could also use this to determine if you use aluminum instead of steel, what happens to this profile? You lightweight the vehicle, you save energy in the use phase, but it could increase in material production. We use this methodology then to look at electrification. But before I get into the study, I also want to point out that you could use this framework to evaluate life cycle cost of a product or the total cost of ownership. And this is work we're also doing with the EV Center. We published this study, which looks at the total cost of ownership in Detroit of a mid-size SUV, taking into account the financing, the fuel, the insurance, etc. You could see for an ICE vehicle, 150,000 over a 25-year period, hybrid electric, 146, a BEV 300, 157K. So in this case, the SUV BEV 300 range vehicle was a 5% increase. If we look at a sedan BEV 300, it was a 2% cost reduction. This is, there's clearly uncertainty around this, but an interesting result was insurance was a top contributor. And Detroit actually has some of the most highest insurance rates compared to elsewhere in the country. But anyway, just to point out that this framework could be used to not only track carbon emissions, we track cost as well. But getting into our study, our purpose was to characterize greenhouse gas reduction potentials of consumer purchasing and operational choices. To do this, we needed to develop a life cycle, a comprehensive model and framework. Our scope was to look across powertrains, internal combustion engine vehicles, HEVs, plug-in hybrid electric vehicles, and battery electric vehicles. And we looked across classes of compact, mid-size, small, and mid-size SUVs and pickup trucks. We also studied use patterns, so the utility factor, the amount of driving in electric mode, drive cycles, whether it's city or highway, took into account cargo loads as well as location. So to develop the model, we first had to create comparable generic vehicle models. And we wanted to have consistent comparison. So we used Autonomy, a tool of Argonne National Lab, to develop functionally equivalent vehicles that defined curb weight, battery size, fuel economy. And then we compared these across the powertrains and the vehicle classes. So the methodology breaks the life cycle down into what's called a vehicle cycle. So that includes the production, assembly, and disposal. So that's the green bars here. And then for the use phase, we track the total fuel cycle. So the production of gasoline starting at the well, and then fueling, and then the combustion of the gasoline. So going from the tank to the wheels. And then in the case of electric vehicles, there we're looking at the electricity, so battery to wheels, as well as electricity generation and charging. And then we take into account the differences in production of the vehicle in terms of batteries and other components. And we use the GREET model of Argonne National Lab as a primary source for some of the data on materials and manufacturing. In this model, we also took into account the fact that the grid is decarbonizing over the life of the vehicle. So we have 2025 vehicles looking out over their life and taking into account where you charge the vehicle, which is shown on this map in terms of grid intensity. So this is CO2 equivalents per kilowatt hour, and you can see the distribution across the United States. And then we track this over time as the vehicle is used over its life. We also take into account temperature effects across the country. As we know, there's bigger influences on fuel economy for the BEV, compared to an ICE. And so this was taken into account in our model. For looking at cargo, we used a model that takes into account or uses a parameter called the fuel reduction value, which is the increase in fuel consumption for driving 100 kilometers and adding 100 kilograms of weight. It's a physics-based model that we applied in the analysis, and these are the different factors of how fuel economy changes with weight, given powertrain, given highway, city, and a combined value. So getting into the results. So first, we're showing here the life cycle greenhouse gas emissions for the vehicle cycle. And it includes production of the vehicle, the materials, the manufacturing, the assembly, disposal, and recycling. That's ADR, is assembly, disposal, and recycling. We also have components, batteries, and fluids. And we're doing this across classes and powertrains. And you could see as we increase the amount of electrification, the vehicle cycle greenhouse gas emissions go up. So going from ICE to BEV 300, here we're looking at the small SUV, it goes up. And then this goes up clearly as we move to larger vehicles like a pickup. The other to note here is that the battery, which is shown in green, accounts for about half of the vehicle cycle emissions for a BEV 300. So this is half of the total production burden, vehicle production emissions. And this is a BEV pickup, but it's the same if we look at a BEV 300 midsize SUV or even a compact sedan. The battery manufacturing is a strong contribution. So if we look at this, you could say that the BEVs are not good as far as sustainability. We're actually increasing greenhouse gas emissions. But we need to look at the next slide. So this is the total life cycle implications in terms of greenhouse gas emissions, which adds the vehicle cycle with the emissions from the use phase. So we have the total life cycle emissions shown here by class and again by powertrain. And we could see clearly that the emissions drop as we go from ICE to BEV. And it actually goes up as you go from BEV 200 to 300 because of that increase in vehicle production, emissions, and use. But in general, the trend is we're decreasing dramatically as we go from ICE to HEV to PHEV. And here we modeled PHEV 35 range and 50 range, and then BEV 200 range and BEV 300 range. For the ICE vehicles and HEVs, use phase accounts for about 90% of the life cycle emissions. So that's this light blue bar. When we move to BEVs, it's 50 to 60%. And when we move to PHEVs, it's 75 to 80% of the emissions, depending on the battery size. So, and what we're reporting here is results based on a national average regarding the temperature effects and grid source for the electricity. So it's a national average. And I want you to focus on the upper chart, which is the life cycle greenhouse gas emissions. And we have plotted across the top the different powertrains, and then we have the different classes going down. And we could focus in on a ICE pickup truck. And that's our reference point, 100% of the emissions. And it happens to be, from the analysis, 486 grams of CO2 equivalents per mile. We could then compare with other powertrains and classes, and I'm going to take you all the way over to a BEV 200 range sedan. And there we're at 81 grams of CO2 equivalents per mile, which is a reduction of 83%. So we're 17% of the pickup. So vehicle choice could lead up to a reduction of 83% for a new vehicle over its life. Going down to the next chart, B, we start with ICE vehicles across powertrain all being 100% and looking at how, if we go to a BEV 200, what the reduction is. And you could see 25, 26% of the original. So we have up to 75% reduction compared to ICE. If we compare the BEV with an HEV, we're talking 68% reduction. Turning to the last chart, if we use the pickup as the baseline, 100% of emissions, everything relative to that is shown. And we can go all the way down to a compact sedan where we see up to 34% reduction in emissions by downsizing the vehicle. We now bring in the spatial dimension. So we're looking regionally at results. And what we have here plotted by different grids, the difference in emissions of CO2 equivalents per mile according to this scale. So here we're comparing an ICE with an HEV, but I want you to focus on if we go from ICE to a BEV, we see reductions in the range of 194 to 356 grams of CO2 equivalents per mile compared to that ICE vehicle. So dramatic reductions across all regions of the country. We could then look at HEV versus BEV, but I'm going to focus in on the PHEV over here, the difference. And now we're in 27 to 67 grams of CO2 equivalents per mile, going from a PHEV to a BEV. But bottom line, we're seeing, as we increase in electrification, we're seeing reductions in emission across all regions. We could then look at the effects of driving patterns. So the utility factor, which is shown on the x-axis, is the amount of driving in electric mode. And that's increasing from 0, which is all gas, to all electricity. The upper graph is ICE, then we have HEV, and we do this for the PHEV. So as you increase in electric mode, you drop in your emissions compared to a BEV 200 and a BEV 300. Looking in Cincinnati, even at 100%, the BEV does better than a PHEV. It's only where you move to a very low grid intensity, like in Seattle, where you're close to 100%, need to be close to 100% driving in electric mode. So you're always driving your vehicle in electric mode, that you can come closer or be slightly less than the BEV in Seattle. Looking at the effect of cargo. So now I'm looking at a pickup truck and I'm adding pounds to the pickup truck from 0 to 2,500 pounds. And again, we're starting out with a pickup truck of 486. If we add 2,500 pounds to the ICE pickup truck, the carbon emissions will go up to 591, or a 22% increase. If we look at the BEV, the increase is 14%. Okay, so this is the effect of adding load to your vehicles, in this case, the pickup, across powertrain. We could look at this effect of cargo on range, and we could see how range goes down with regard to the BEV pickup truck. And looking at it in Chicago versus San Francisco, we see a range for the BEV 300 decreases by 106 miles, or 35%. In the moderate climate of San Francisco, and in terms of the PHEV, we have reductions to 34 and 24 miles respectively, with an added 2,500 pound cargo. So in terms of conclusions from our study, we have shown that increasing electrification results in emissions reductions across all regions of the country. And this is a new finding. And it's been shown that BEVs can reduce, but there are concerns about where you charge. Here we're showing, and it's not just BEVs, PHEV, if you go from HEV to PHEV, you're going to get reduction. National average, we range from 81 to 486 grams per mile. In terms of the emissions of the vehicles we studied, the reductions are 75% in going from ICE to BEV 200 across all classes, up to 34% reductions looking at downsizing for each powertrain. So within a powertrain, going from pickup to sedan, up to 34% reduction. When we combined powertrain electrification and downsizing, we can get 83%. So that's going from a pickup ICE to a BEV sedan. Regionally, across the US, we found 34 to 300, 10 times that, 341 grams, depending on your grid, your vehicle class, and battery size. In the low grid areas, the BEV 200 and compact sedan achieved 90% lower emissions than the ICE pickups. Even in Arizona, which is the most intensive grid, the BEV pickup and compact sedan had 40% and 61% respectively lower emissions than the ICE pickups. Moving to recommendations. So clearly we recommend BEV over a PHEV for the greatest greenhouse gas reduction, unless there are challenges with regard to infrastructure for fueling, where you want flexibility with the gas engine. The BEV does achieve a significant reduction. BEVs give you 72% lower emissions than the ICE, and the PHEV 50 has 58% lower greenhouse gas emissions compared to the ICE. This is based on national average. In case of the PHEV standard utility factors. few other things I pulled out of the paper, recommendations. You want to diversify your fleet when you can. For example, we shouldn't be driving our large SUVs to commute to work. If you're commuting by yourself, you would commute in a BEV sedan. So you do want a diverse fleet if you have more than one vehicle. And we looked across archetypes. So we looked at people vacationing, we looked at commuters, we also looked at contractors. So clearly BEV pickup can reduce your emissions, and there's many other clear benefits in terms of BEV pickups for contractors. What I also want to point out here is we're actually just finalizing an online tool for users to be able to calculate the emissions from their choices. So it's an online calculator that will be launching soon. We're going to be launching it with the paper once published. And it's just showing you, this isn't the final format, but just a prototype. You put in the location where you're charging your vehicle, or where you're, have a BEV or a ICE vehicle, and then you go down to select your vehicle choice. So in this case, we selected a midsize SUV, ICE, and we're going to compare it with a compact sedan, a BEV 200-mile range vehicle. You then get results out of the model, and it shows what the emissions are over the life. So you see the SUV emissions, 87 metric tons per CO2 equivalents, compared to the compact sedan of 14 metric tons, difference of 73 metric tons. We also allow you to compare not only the two vehicles you selected, but you get to see how your selections compare with alternatives. So all the other powertrain class options, which are shown here. So these were the two that we picked: 411 for the midsize SUV, 73 for the BEV sedan, and what the percentage difference is relative to that pickup. But then here are all the other vehicles. And final slide here is the map that we also present. So for all the grids, we show, and this was Dane County, Wisconsin is where we focused on. It shows what the emissions are for the first vehicle, the second vehicle, and the difference. And then we show all the other grids in the country, what the difference is between those vehicles. Okay, so that's what I wanted to present here on our study. And at this time, we're going to open it up for questions that I think Alan might be helping me and moderate. And really look forward to your questions, your feedback. And yeah, I guess I had one other slide. Sorry, just to point out, besides what I'm going to answer in terms of questions, we have a fact sheet that we developed on EVs. We have many other publications on life cycle of EVs and other vehicles. And if you want to get a hold of me, I have my email here. But I am going to now just turn it over to Alan to moderate.
Well, Greg, thanks so much for an outstanding presentation, and consider this virtual applause. People can now either use the Teams raise hand or put your questions in chat, and Jamie Reckliff, our communications director, will guide the question.
Sure, great job, Greg. Everybody, if you want to add more questions, chat might be the easiest, but as Alan said, you can also raise your hand and we'll let you ask it live. The first question we got from Harvey was, given the carbon intensity map is dark blue in Texas and Oklahoma, I assume that's because of wind generation. Is that correct?
Yeah, let me I should have left these back up here. So Harvey, I think you're referring to this map here. Yeah, this is Texas here. West Texas is all the wind. If you look up in Seattle, we have a lot of hydro. California has a lot of natural gas. We could look at these regions here that are in yellow. Ohio, a lot of coal. Montana, Wyoming, a lot of coal. Wyoming has, or Montana has also some wind. Yep, thank you.
Harvey also asked about the earlier study you mentioned with Ford. Was the residual value considered?
Were we talking about the
Cost of
life cycle
ownership.
cost study or?
Cost of ownership.
Or I'm sorry,
Cost of ownership.
cost of ownership study. So cost of ownership study, basically we took it, sorry, I just mouse. Yeah, so we took it to the full, basically life, depreciated fully over the life. We're doing a study now where we're actually looking at used vehicles, and we're scraping data and getting used vehicle prices to get depreciation so we could see how it depreciates over time. But this is looking at over the total, 25-year life.
But so it's a single user or multiple users. Residual value is the value that the financial industry assigns to a vehicle as it comes off lease. So if you
Yeah,
had
no, this is going beyond lease. So this is looking at, this would, generally going to involve multiple users. So
Okay.
it's over the total,
yeah.
25-year life.
With no
So-
change of ownership cost, Harvey. It's a direct depreciation.
Okay.
Yeah,
So, okay.
so it's got the financing shown, here in yellow, and then it's, looking at all the other costs, annual fees, registration, repairs,
Yeah.
maintenance.
Yeah, I got all that. I just wanted, I was looking for a differentiation impact on brand.
Yeah, so this was looking at, we're in this particular study, we're looking at generic models. So we weren't differentiating by brand. In the study we're doing now, where we're pulling data and scraping, we're looking across different brands. So these are generic vehicles that have certain fuel, generic fuel economies, so that we could look across these consistently.
And then another question was related to the time of use charging plan from the utility company. Is the cheapest time of use also the cleanest?
So that will depend, but we did look at the effects of charging at home versus public charging, and there's significant differences. It could be, twice, 3 times as much to public charge than at home. So we do have those scenarios in this paper. And as far as when you charge, we've done a lot of work on when you charge, in terms of, nighttime, daytime, what those effects are. And we've actually done optimization on when you should charge depending on where you're at. And it does depend on what grid you're in.
Any other questions from anyone in our audience?
Well, I'd like to thank everybody who joined us today, and just want to make a few closing remarks. First, for those of us who own electric vehicles, and there are various reports out there and postings about, oh, it costs much more in CO2 and energy to make the vehicle. I mean, and depending where you drive, it's not helping the CO2 emissions. To me, the key part of this study, in terms of the high level takeaway, is if you choose to buy a BEV over an ICE and over a PHEV, anywhere in this country, any size vehicle, you are not only getting a better vehicle, but you are improving the CO2 footprint of the United States. And I think that's an important message that we all can carry with us. The slides will be available, and we are recording the presentation, so it will be posted later. And hopefully in the not too distant future, the review process of the formal published paper will be complete and it will be available. And we'll inform people when that occurs. So again,
Alan, could I
please.
say just one
Yeah,
other
please,
thing,
Greg.
building on what you said?
Please.
So I showed what we need to do in terms of trajectory of reducing carbon emissions. We need to cut emissions in half by 2030, get to net zero by 2050. We've actually done modeling with very aggressive goals of 50% sales by 2030 of EVs, full grid decarbonization, or close to it by 2035. And we can get close to basically being on track with that trajectory. But 50% sales by 2030 is aggressive. And we're somewhere around 10% now. But we need to do this because the more we delay in terms of decarbonization, the greater the damages and the costs. And we're seeing those costs, in California. Those are only going to increase. IPCC wants us to, keep temperatures below 1.5 C. We're going to go above 1.5 C. We missed that target. But it doesn't mean we let up on the EV accelerator. We need to, that is a key strategy for decarbonization of transportation. And, not everybody could afford new vehicles. And so those that are buying new vehicles, this is my sales pitch, should be buying BEVs, bringing those in. And so we could turn over the fleet of vehicles. So very important here that we continue to accelerate those sales. And again, there's myths out there about EVs are worse for the environment. This shows, with regard to carbon emissions, the clear advantages. There are some trade-offs, but if you look at sustainability, the biggest challenge we face in terms of sustainability is climate change. And that's what we're locking on here. We look at other factors like supply chains and where the battery materials are coming from. That's part of work we're doing with the EV Center. But just as far as emphasis and dispelling myths, we hope this will help do that.
Yep, and the sooner this gets formally published, the better, Greg. So again, thank you for joining us. For those of you that have not yet become an affiliate of the EV Center, you can go to our website and do it, but also please mark your calendars for the evening of April 1st and all day on the 2nd. We will be having our first annual symposium. We've lined up a great set of speakers, both internal and external, to the university. It is free to attend, and we are trying to see how many people will come. So please register, as well as becoming an affiliate of the EVC. With that, one more time, Greg, I'd like to thank you for a wonderful presentation, and thanks everybody for joining us.
Thank you.
Jamie, do you want to say how the